Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Welcome to the debate. So imagine for a moment that you are an airline executive. You've just purchased a fleet of state-of-the-art commercial aircraft at a staggering 50% discount.
Okay, sounds like a pretty great deal so far.
Right? They have gleaming aluminum bodies, plush interiors, the absolute latest avionics, but there is just one catch.
Oh, let me guess, they don't have FAA certification.
Exactly. Which means you can't board a single passenger.
Right, so you've essentially just bought the world's most expensive lawn ornaments.
Precisely. I mean, they cannot legally carry passengers, they cannot be insured, and they absolutely cannot leave the tarmac. You saved millions on the initial capital expenditure, but the asset itself is legally barred from operating. And we are seeing this exact same illusion of savings happening right now in the North American biomanufacturing industry.
Yeah, you're talking about the strategic procurement of bioreactors. The globalization of supply chains has completely transformed how we source process equipment. I mean, we're looking at a spectrum that ranges from, 10-liter laboratory benchtop reactors all the way up to these massive 200 cubic meter commercial fermenters.
Yeah, and the market is effectively split right down the middle. On one side, you have the premium European vendors, mainly in Germany, Switzerland, and Italy. And on the other, you have these cost-advantaged Asian manufacturers in China, India, and South Korea.
Which naturally brings us to the central question we are examining today. Does the 30 to 60% upfront CapEx or capital expenditure savings of sourcing bioreactors from Asian manufacturers actually justify the substantial regulatory and life cycle risks? Or is that premium European tier the only genuinely viable path to ensure GMP certifiability and, avoid a catastrophic asset write-off?
Right. And my position is that the premium European systems are absolutely essential for North American biomanufacturing. That supposedly high upfront cost is completely justified because, frankly, the compliance gaps and the hidden lifecycle risks of low-cost alternatives consistently result in total costs that are 2 to 3 times higher than if you had just bought the premium system in the first place.
And my position is that a hybrid sourcing model, one utilizing Asian fabrication, is actually the strategic ideal here. I argue that organizations can safely leverage the massive global manufacturing efficiencies of these cost-advantaged tiers, provided they employ really rigorous North American quality assurance oversight and final certification processes.
Okay, well, let me lay out why the European tier is the unquestioned benchmark. When you are operating in a good manufacturing practice or GMP-regulated environment, oversight from Health Canada and the FDA is incredibly rigorous.
Oh, absolutely.
Right? When you buy a commercial fermenter from a German or Swiss vendor, you're not just buying stainless steel. You're buying a comprehensive documentation package that basically proves to the regulator that your process is inherently safe and reproducible.
Sure, but we have to look at the reality of modern manufacturing. Asian suppliers represent a profound strategic cost advantage tier now. I mean, the quality maturity in countries like South Korea and India has improved markedly over the last decade. They are offering up to 60% CapEx savings.
Wow.
Yeah, and significantly accelerated delivery timelines.
That's an interesting point, though I would definitely frame it differently. To evaluate if sourcing from Asia is truly viable, we have to tackle the most common point of critical failure in procurement first, which is mechanical compliance. Specifically, pressure vessel certification.
Because, at the end of the day, a bioreactor is essentially just a highly pressurized vessel.
Exactly. And if it fails, it is catastrophic. In Canada, there is a rigid mandate for what is called the Canadian Registration Number, or the CRN, under the ASME Boiler and Pressure Vessel Code, Section 8. And so many of these low-cost Asian systems lack this ASME stamping entirely.
Wait, before you move on from that, just for anyone listening who might not be a mechanical engineer, what exactly does the CRN practically require? Why is it so hard for an overseas vendor to just stamp it and be done with it?
Because it isn't just, a sticker you apply at the end of the line. The CRN requires an exhaustive, fully documented trail of exactly how that vessel was built.
Right, the material trace.
Exactly. We are talking about tracking the specific heat numbers of the raw steel, verifying the exact qualifications of the welder who did the work.
Which is a huge pain to track down after the fact, by the way.
Oh, it's virtually impossible. And you're conducting radiographic testing, literally X-raying the weld seams to ensure there are no microscopic voids that could burst under pressure.
And your argument is that Asian manufacturers just don't do this?
My argument is that if they don't have the ASME certification, provincial inspectors will immediately red tag the equipment. It fails pressure testing and inspections on arrival. This is exactly like buying that deeply discounted commercial aircraft without FAA certification.
Right.
The upfront savings mean absolutely nothing if the inspector legally bars it from operating.
But many of these Asian vendors have PE certification, right? Which is the really stringent European pressure equipment directive. It's not like they are building these things in a completely unregulated vacuum.
I see why you think that, but let me give you a different perspective. Even if an Asian vendor has PED certification, PED alone is legally insufficient for North American installation or insurance.
Really?
Yes, you simply cannot bypass the absolute regulatory floor of the ASME Section 8 and the CRN. It doesn't matter how good the European standard is, if it's not the North American standard, you cannot turn the machine on.
Well, I come at it from a different way. You are assuming that sourcing from Asia means accepting the equipment as is, out of the box, with whatever stamping the local factory decided to apply, and frankly, that is an entirely outdated view of procurement.
How so? I mean, if the factory doesn't have the stamp, they don't have the stamp.
Because the hybrid model explicitly solves this stamping gap. In a modern hybrid approach, you don't just order a vessel, put it on a cargo ship, and cross your fingers hoping it passes a provincial inspection when it arrives in Toronto or Boston. You deploy qualified North American engineering teams or third-party auditors directly to the fabrication site in Asia.
Wait, so your grand solution for saving money is flying entire teams of engineers across the world to watch people weld?
Exactly. The ASME, VII, and CRN requirements are integrated into the design and welding protocols from day one. The material traceability, the welder qualifications, the X-raying of the seams that you mentioned, all of it is overseen and documented according to North American ASME standards in real time.
That sounds incredibly complex.
It takes coordination, sure, but by the time that vessel arrives for commissioning, the requirements are already met. You are leveraging their vastly lower labor and material costs while imposing our strict regulatory framework.
I'm not convinced by that line of reasoning because it introduces a massive hidden layer of complexity. You are moving from simply buying a product to essentially managing an international construction project. And that brings us to the daily operation and integration of the equipment. The operational life cycle of these cost-advantaged systems often destroys their initial value because of hidden engineering risks.
Okay, what kind of hidden risks are we talking about here?
Let's start with utility mismatches. You import a system from Asia, and it is wired to operate on a 50 Hz electrical frequency. But the North American power grid runs on 60 Hz.
Which sounds like a pretty simple electrical conversion, right? Just swap out a transformer or add a variable frequency drive?
If only it were that simple. Running a 50 Hz Asian motor on a 60 Hz North American grid isn't just a plug issue. It's like playing a vinyl record at the wrong speed. The motor spins 20% faster, and suddenly your impellers are whipping the cellular broth way too hard.
Ah, which throws off your oxygen transfer rates.
Exactly. The agitation profiles go completely chaotic, and the delicate biological cells you are trying to grow are literally sheared apart by the turbulence. Furthermore, your pumps start to cavitate.
Let's clarify cavitation for a second. That's when the pump blades move so fast they create tiny vacuum bubbles in the liquid. And when those bubbles collapse, they create shock waves that slowly eat away at the metal.
Spot on. It destroys the pump from the inside out. Fixing this requires extensive, highly customized site modifications. And, that's just the mechanical side. We haven't even touched automation incompatibilities. North American data integrity requirements are governed by the FDA's 21 CFR Part 11.
Right.
which is essentially the digital chain of custody, making sure that electronic records and signatures are entirely tamper-proof.
Right.
If a temperature parameter drops by 2 degrees at 3 a.m., the system must securely log exactly who acknowledged that alarm and what they did about it. If the Asian vendor's PLC or SCADA software is essentially a closed black box that doesn't natively align with these strict audit trail requirements, the FDA will shut you down.
Wow.
You end up having to rip out the entire automation brain of the bioreactor and rebuild it from scratch.
I'm sorry, but I just don't buy that. Let me tell you why. You are calculating the cost of these retrofits as if they completely erase the initial savings, but the math simply doesn't support your premise.
Rebuilding a SCADA system and retrofitting industrial motors isn't exactly cheap.
No, it's not. But a 30 to 50% capex savings on a multi-million-dollar commercial fermenter translates to a massive financial runway. We are talking about millions of dollars in upfront savings. That provides more than enough capital to fund local engineering integration, upgrade the automation software to perfectly meet 21 CFR Part 11, and swap out utility components for 60 Hz compatibility. And you still come in well under the final cost of a premium European unit.
But you are also inheriting a broken spare parts ecosystem. If a non-standard proprietary component breaks on that Asian system, you are waiting 4 to 6 weeks for a replacement to cross the ocean. And in a GMP facility, every day of downtime costs hundreds of thousands of dollars.
And that is exactly where the strategic opportunities of the hybrid model shine. We are seeing incredible advancements in modularization, skid-mounted, or turnkey systems, where the Asian manufacturer works directly with North American contract development and manufacturing organizations, or CDMOs.
So they are essentially pre-engineering the systems to accept our parts?
Exactly. Through joint design programs, they pre-engineer the skids to accept standard North American components for all the critical wear parts, the valves, the seals, the sensors. That completely solves the spare parts ecosystem issue you just mentioned. You get the Asian steel, but the local replacement parts.
I hear the theory, but that drastically underestimates the stringency of GMP validation expectations at scale. It is one thing to retrofit a valve. It is an entirely different endeavor to prove to a regulator that the retrofitted system functions identically to the originally validated design.
You're referring to the IQ, OQ, PQ documentation burden.
Yes. And for those listening who might not live in validation documents every day, that stands for installation qualification, operational qualification, and performance qualification.
The holy trinity of GMP.
Exactly. Installation asks, is it built and plugged in correctly? Operational asks, does it spin, heat, and cool exactly as designed? And performance asks, can it consistently produce the actual drug without variation? When we talk about this level of validation, we are talking about microscopic perfection.
Such as surface finish standards.
Exactly. The surface finish of every wetted part. Every square inch of stainless steel that touches the product must be verified to an RA of less than or equal to 0.5 to 0.8 micrometers.
To visualize an RA of 0.5 micrometers, imagine a surface so flawlessly mirrored that not a single microscopic bacterium can find a scratch to hide in.
Right, because if there's even a microscopic groove, bacteria settle in and form a fortress, a biofilm. And biofilms can survive your cleaning cycles and completely ruin a $10 million batch of biologics. This is why cleanability must be proven through rigorous clean-in-place and steam-in-place, or CIP and SIP, studies with exhaustive residue data.
Where you aren't scrubbing the tanks by hand, but blasting them with highly calibrated chemicals and pressurized steam.
Exactly. And for GMP commercial scale, meaning vessels greater than 10 cubic meters, the sheer complexity of proving that perfection across a retrofitted, hybridized machine is just staggering. Premium European systems come with these validation packages basically ready to execute out of the box. They remain the benchmark because the risk of a single documentation gap halting a commercial drug launch carries a financial penalty far, far greater than any initial capex savings you got from buying the Asian steel.
That's a compelling argument. But have you considered how these sourcing strategies apply across the entire scalability spectrum? You are focusing entirely on massive GMP commercial scale, these 200 cubic meter behemoths.
Well, because commercial scale is the ultimate goal of biomanufacturing. That's where the drugs are actually made for the public.
Absolutely tip toward the premium European systems. The sheer density of the IQ, OQ, PQ documentation required makes the turnkey European solution highly attractive.
But a biomanufacturer's facility is not just comprised of massive commercial fermenters.
You're talking about the pilot and demonstration scales.
Exactly. Look at the recommended procurement strategy across the product lifecycle. For pilot-scale systems between 10 and 500 liters, high-quality Asian bioreactors with pre-certified designs are incredibly cost-effective. You don't need a Rolls-Royce to learn how to drive. For demonstration scale, spanning 1 to 10 cubic meters, the hybrid sourcing model ensures validation and regulatory readiness without completely paralyzing a company's budget before the drug is even approved.
But if you mix and match vendors across scales, don't you create a nightmare for technology transfer? I mean, moving a process from an Asian 500-liter pilot tank to a German 10,000-liter commercial tank introduces entirely new variables.
Actually, I'd argue it builds critical internal competency. Mastering this hybrid sourcing at the earlier pilot and demonstration scales is essential for global agility. If a biomanufacturer only knows how to write a massive check for a premium turnkey European system, they essentially outsource their own engineering intellect. Right? They lack the internal agility to scale globally. The hybrid model forces a company to build internal competency in QA oversight and mechanical integration, making the organization fundamentally more robust and competitive in the long term.
But that internal competency you are praising is essentially forcing a biomanufacturer to become an equipment engineering and regulatory audit firm. That distracts entirely from their core mission, which is discovering and producing life-saving biologics.
I don't see it as a distraction. I see it as owning your process from the metal up.
Well, let's summarize where we stand, because I think we have clearly defined the boundary lines of this debate. For North American biomanufacturers, procurement is a stark choice between being compliance-ready from day one or deliberately taking on retrofit risk. In a regulatory landscape governed by Health Canada and the FDA, CapEx savings must always remain secondary to system certifiability, data integrity, and process validation continuity.
Because you view the European systems as an insurance policy.
Absolutely. The premium European systems provide certainty. When dealing with highly pressurized vessels, strict software compliance, and microscopic material traceability, certainty is not a luxury. It is a fundamental requirement for market entry.
And I would summarize by saying that the modern biomanufacturing landscape requires more nuance than simply writing a larger check to guarantee certainty. An integrated procurement framework, one that engages quality assurance, engineering, and regulatory teams from the very inception of a project, allows organizations to treat bioreactors as the GMP critical assets they are, while still safely leveraging global cost arbitrage.
By utilizing the hybrid model.
Exactly. The hybrid model proves that you can enforce North American regulatory standards on cost-advantaged global manufacturing. You send the auditors, you oversee the welds, you upgrade the software. It takes effort, yes, but the economic and strategic advantages of building that robust, diversified supply chain are absolutely undeniable for a company looking to scale efficiently.
What is incredibly clear from both of our perspectives is that procurement is no longer a purely financial, ledger-based decision. Successful sourcing requires evaluating vendors across a highly complex, 9-dimension procurement checklist.
Oh, you really have to look at everything. You have to evaluate the logistics of shipping massive steel tanks, the harmonized system codes for customs clearances, the factory audit results right down to the life cycle support and whether they have a local service presence in your time zone.
Absolutely. And when you factor in the deep complexity of importing biological materials alongside this equipment, where you might have Environment and Climate Change Canada conducting oversight under CEPA, the Canadian Environmental Protection Act, the necessity of viewing these supply chain decisions through multiple regulatory lenses becomes incredibly apparent.
There is far more technical depth to explore here, particularly regarding the specific methodologies for conducting factory and site acceptance testing and how to properly score supplier risk before you ever sign a contract.
Which means ultimately, we are right back on the tarmac where we started. You can hunt for a 50% discount on the hardware, but before you sign that purchase order, you have to be absolutely certain your engineering and QA teams have the capability, the knowledge, and the regulatory foresight to get that aircraft legally certified and actually in the air.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Ernala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.